Okay, go.
Good time of the day, everyone. This is Ivan from EPIC, the European Photonic Industry Consortium, and today we prepared for you the new episode of EPIC members' new product release. And join me today in spectating these 6 presentations that found the agenda for today. We'll hear the presentation from Hummink, from Laserpoint, from the EPIC member VPIphotonics, as well as Silicon Light Machines, and EPIGAP, as well as SCIVAX. And without further delay, I would like to invite the first speaker of today's event, Pascal Boncenne, the co-founder at Hummink. Please, Pascal, whenever you're ready.
Great. Can you hear me well?
Yes, you just need to go full screen.
Here I am.
Who's yours?
Okay, let's go. So hi, everyone. I am Pascal. I am co-founder of Hummink, and we do additive manufacturing at the nanoscale. To start with, a first video of what we do. And here it's an example of deposition of silver with a resolution of 1 micron that you can see at real speed. And this is a breakthrough technology that we have developed and that enables such deposition with any type of material. The question you may have now is, what's under the hood and how do we do this? So here's just a close-up on our technology, which is derived from AFM technologies. We basically replace the probe of an atomic force microscope by a glass capillary that you can see here that is filled with liquid. And we replace a traditional resonator by a macro resonator, which is this big tuning fork that you can see here, so that its oscillation properties are not impacted by the weight of the pipette. So we attach the pipette to the resonator, have it oscillating at a defined frequency. We put the substrate beneath on an XY table that will come close to the tip of the pipette until the formation of the first drop of liquid formed by capillarity. And hence we move the station on the XY axis to ensure the deposition of your need. With a unique combination of feature. As I said, we can deposit with any material on any surface and resolutions that can go from 100 nanometers to 50 microns. We also have a 20 nanometer XY precision, and as I said, a deposition rate that is already fast and up to 10 millimeter per second. The beauty of the technology is that there's no external source of energy that is needed. There's no metallic reaction. There's no UV light. It's only capillarity that will drag the liquid out of the pipette and ensure the deposition. So today I wanted to share with you the product release of our first equipment, which is called the Nazca machine. And here you have a small video that shows it. So the Nazca machine incorporates all the benefits of the technology that I previously described. It's a tabletop equipment. Here you can change the ink and place any type of pipette. The size, you decide the size, you decide the type of ink you want to use. You just use a very easy to use software, press start, and you're good to go. This is a unique equipment that unlocks resolutions down to 100 nanometers with unique versatility in terms of substrates and material for the deposition. The working surface is 16 centimeters. And you can use this for several types of applications, such as micro LED, packaging, but many more.
XS1? Yes. Yeah. Yeah.
So this is really a product designed for R&D purposes, and designed for any labs that can work on several topics with one single tabletop equipment. As I said, we're able to deposit any material, so we mostly work on silver, copper, gold, but also graphene, polymers, or quantum dots. We can deposit on any surface, such as silicon wafers, glass, or flexible substrates, and we can use any type of shape, any type of design that can be 2D, but also 3Ds, like these pillars that you can see here. And here we're talking about silver pillars. So just a few words on the main use cases we have with this equipment. On the left-hand side, you see on-domain interconnects. So we have partners and clients who struggle to build, soldering connection between miniaturized components, and the agility of our solution and the precision is quite unique. And second, on the right hand, we can also provide a unique surface patterning on raw substrate with unique materials, such as the quantum dots that I previously showed, and once again here with unique resolution. So that's it. I wanted to fit into the 5 minutes limits. I hope you enjoyed this presentation, and I'm all ears to any type of question you may have.
Yeah, nice product. Thank you very much, Pascal. This is exciting to see this machine in operation. And so right now, everyone who's connected with us on Zoom is welcome to ask any quick questions before we jump to the next presentation. So you can just use the button raise hand or just unmute yourself, and if you have a question. Yeah.
Good morning. My name is Sarmad. I just joined, so a little bit late, so I apologize. Quick question. This machine, can you deposit also glass?
Do you mean deposit on glass or deposit glass?
Glass, SiO2.
We have never deposited the glass. We have to, the only constraint we have is that we had to formulate it into a liquid. So, and we provide this knowledge to design our own inks. So we have never done it, but I'm curious to hear a little more about your application. I'm sure we can develop something related to it.
Okay, thank you.
Yeah, now Sergio from Laserpoint, please go ahead.
Yeah, good afternoon, Pascal. Just a couple of quick questions. Do you plan to have multi-spot for parallel? I suppose, yeah, that's great.
Yes.
And
yes.
the other thing is, do you need to have a kind of sintering of the material, which is the density that you are of the material that you're going to deposit?
So first question, yes, we're already working on multi-nozzle. The product I wanted to share with you today is just the first equipment that we are planning to produce, which is for R&D purposes. And the next step will have some more automation, in the software detection, and also the multi-nozzle. And second question concerning sintering, it's really case by case, depending on the material, but yes, mostly for the silver, copper, gold inks, you will need sometimes some sintering in order to have it so the ink can be conductive. It's not necessary to ensure the deposition, but it's a post-processing that can be required for some applications and some inks.
Yeah, thank you.
You're welcome.
All right. Is there any more questions? Because if not, thank you again, Pascal. And I'd like to pass the word to our second speaker, who was actually just asking a question. So Sergio Pellegrino, a partner and the R&D director at Laserpoint, will tell us about HarshMax, the new and patented optical pressure sensor for harsh environments. Please, Sergio, the floor is yours.
Everything is okay. Can you see the screen correctly?
Yes, all good.
All right. So thank you, Ivan. This talk is delivered by Laserpoint. I'm Sergio Pellegrino, I'm company partner, and managing the R&D activity of the company. The topic is about a new optical pressure sensor for harsh environment. I'll be more specific later. Okay, was a little bit late. Just a briefing introduction to Laserpoint. Maybe you know us as a manufacturer of laser power and energy meters, from, let's say, milliwatts to multi-kilowatts, and more recently, we have introduced a new family of energy meters that are able to measure fast and ultra-fast lasers at very high repetition rate, from microjoule to several tens of joules. In the recent years, we have started a product diversification that was based on know-how, company know-how on fiber optic technology. This brought us to the development of a family, at least father and mother at the moment, which we call it, that are optical pressure sensors for harsh environment, where harsh is high pressure, high temperature. So we are introducing to the market of plastic extrusion and injection molding this new worldwide patented sensor that we call HarshMax. Here's the picture of the system. You see, maybe you can see my arrow. On top is the sensor itself that goes to the extrusion machine. This is the tip, which is the sensing area, which is in contact with the molten polymer. The signals are sent back and forth by optical fibers, and that can be 100 meters far away from the brain of the system, which includes all the optical and electronical parts. So the brain is here. The sensor itself is just, in short, stainless steel and glass. So for people, for those who are not acquainted on the application, the plastic extruded machines schematic is shown here. Typically is a machine where there is a feed of polymer pellets of different materials. The extrusion, you can extrude a lot of different materials which are melted, pushed toward the end by large screws, and then the product is delivered. What is encircled is all the sensing. This is full of sensors. Most of them are pressure sensors and some temperature sensors as well. And this is where our sensor goes. So just a quick overview of the competitive advantage of the HarshMax. Beside the fact that it is patented, is eco-friendly, because there is no mercury, there is no oil, there are no toxic elements. Again, the head is just stainless steel and glass. The head is passive, so this is good. This passive part is those which is in contact with the harsh environment, pressure and temperature, up to 1 kilobar in our product portfolio, and 300 degrees. Another key point is that the rack with optics and electronics is remote, so just connected by an optical fiber. So it's far from the harsh part and dirty part of the job, and then it's easy to plug and unplug the sensor for eventual replacement. At the end, it has a low maintenance cost because of the high sensitivity of this system. The formable diaphragm is relatively thicker than competition. Then it's more difficult to have it damaged. So most of our technology is based, realization technology is based on laser welding technology. There are several steps of laser welding technology here, just to show you which is our equipment in R&D lab. And here are the babies. If you can see my arrow, this is the long body and short body. Long body TP is the standard for plastic extrusion machines. Short body is for different applications. Some of those I didn't mention. I'm not going to mention in this talk yet, maybe later. Then we are close to the end. I hope I am in time. And just to show you an example of sensor specification table for the 200 bus model. That sensor should stand to 1.5 times the maximum rated pressure. So in this case, it's standing 300 bars. Again, 300 degrees C. So here is the response of the sensors: pressure versus voltage, output voltage. You see that is exceptionally linear, no hysteresis, which means that for us it makes easier the realization, because we do not have to apply complex calibration algorithm to the system. So in conclusion, we are introducing to the market of plastic extrusion and injection molding a new sensor, optical sensor, pressure sensor, we call HMAX, which is patented, eco-friendly, passive and remote electronics, a low maintenance cost. And thank you very much for your attention.
Thank you for introducing the product, Sergio. It is now open for questions. If anyone in the audience needs more details, please push the raise hand button. I was actually wondering myself, Sergio, so how is the precision of this kind of optical pressure sensors as compared to other pressure sensing technologies? Let's say the traditional mechanical ones.
is a fraction of a millibar, absolute.
All right, and that's much higher, I guess, than mechanical.
Oh yeah, definitely.
Okay. Anyone else? If not, thank you again, Sergio, for the present. Okay, wait a minute. There is a question from Lucas.
Yeah, hi. Thank you for the presentation. I was just curious, was there any reason you went to a direction of a sensor especially designed for a harsh environment? Did you see like an industry, a need for it, or some sort of a really interesting new application that you have in mind?
Well, this is let's say combination of the two, as I mentioned in the first slides. This is based on a proprietary know-how on optical fibers, but this really came from market needs. Is a large market, very few players with standard technologies, which have some limitation. For example, at the maintenance level, they need to change quite frequently the head because they are going to damage either the sensing part or others. So this new concept is going to answer to those needs.
All right, thank you.
All right, thanks again for the presentation, Sergio. And the next speaker of the session is Chris Maloney, the Director of Business Development at VPIphotonics. And he will tell us about the new machine learning framework for designing and implementing deep neural networks. Please, Chris.
Yeah, thanks, Ivan. Yeah, you can see my screen okay? All right, I'll assume you can.
Yes,
yes,
we can.
Yeah, as Ivan mentioned, I'm Chris Maloney. I'm the Director of Business Development at VPIphotonics, where we provide photonic design, automation, and simulation software. And so we're excited to announce today the release of VPI Toolkit Machine Learning Framework, which is a framework for the easy integration of machine learning algorithms into your simulations. So just to start, the machine learning framework, it's a way to automate statistical models using algorithms to make better predictions. So what we've implemented is this powerful framework into the software using open source Python-based deep neural networks. And this is an add-on to all of our products in the VPIphotonics design suite. So just to get you started with the workflow, how does this actually work is you start with VPI Design Suite, you simulate, you create a design for a component or a system. So as you would in the typical software. And then we have an API where you can define your machine learning algorithm. And so we actually represent the data so you can store large sets of data using an HDF5 file format. And then what we can do is take our machine learning algorithm, we generate data, we generate simulation data for it, and we actually use that data to train the machine learning algorithm. And so in the end, we end up with a machine learning model, and then we can use that integrated machine learning model and algorithm back in your simulation again. So as I mentioned, this fits into VPIphotonics design suite. So we do have tools at many different levels of abstraction, from devices all the way to networks. But this fits in VPIphotonics design suite, which includes transmission design, so optical system, VPI transmission maker, optical systems, as well as component design. So if you're designing, let's say, a fiber amplifier, you can use it with VPI component maker fiber optics. Or if you're designing a photonic integrated circuit, it can be used in VPI component maker photonic circuits. And really where we started with this is at the optical transmission system level. So I'll actually take you through an example of that today. So here's the first example, just to give you an idea of how this works. This is where we started, a deep neural network-based equalization for NRZ, non-return to zero, optical transmission system, so typically used in short-reach applications. So just to walk you through the schematic, we have a NRZ transmitter on the left side, so we have a bit stream of ones and zeros. We have a laser that's being modulated. We have a Mach-Zehnder modulator here. That signal passes through a fiber, and it's received on the other side. And then there's some analog to digital conversion, and we have some output. So the way that we works is we have these digital data extractors. So we have an input and an output. So on the input side, it's our bit stream of ones and zeros. So that's the ideal case, that's the ideal signal. And on the output, we have the signal after it passes through Mach-Zehnder modulator, the laser passes through the fiber, it's received on the other side by some PIN photodiode, and there's some analog to digital conversion done. So the output signal has been skewed. So that's our input, that's our output. That's what we actually load into our deep neural network model algorithm. And we have what we've done in the software is expose the hyperparameters. So we can specify the number of layers in your deep neural network model, the number of neurons, the number of epochs that are used to converge on a model. And so we pass this large training data set into the algorithm to define some model. And then what we use we then use that model to do some equalization. So you have ones and zeros on the input, and that same signal is probably not what you see on the output, but we can train this model to do equalization. And so you can see the output here. So you have the original sequence in blue, after passing through the deep neural network equalization, you have your bit stream in red. So you can see it's pretty close to the original signal. So this doesn't have to be used just for direct detect systems, but it can also be expanded to coherent systems as well. One more example, and this is for those of you who have some device in the lab that you have a lot of experimental data for, but maybe you don't have a model generated for it. And so we'll take you through an example of looking at a specific component, in this case, erbium doped fiber amplifier. So in the software, we actually have a pretty detailed physical model for this. So there's doped fiber models. There's 2 of them in this configuration. There's also 2 pump lasers used as well. But maybe you don't know anything about your device at this point. So in the schematic, you can see there's 4 channels. There's 4 lasers being multiplexed together. That optical spectrum is actually used as our input in this case. And then that signal passes through your fiber amplifier, and then we have some output. So we collect the inputs, we collect the outputs, we train our deep neural network model. And what you can see here is the green lines actually show the simulated fiber amplifier model, and the blue lines show the model using the deep neural network model. So what you can imagine is, instead of having this EDFA, maybe you have some device in the lab, you have tons of data for that. And instead of having a physical model, you actually represent it as a deep neural network model. And then what you can do is, in the simulation world, push that device to the extreme so you don't actually damage your device in the lab, and explore different configurations with it. So it's pretty flexible framework that we have here. So there's a lot of different applications for this. I took you through 2 of them. It can be used for fiber nonlinearity compensation, optimizing system parameters, or estimating quality of transmission. And so what we've done is we've made it easy for you to collect large data sets and store them, and actually have access to these deep neural network hyperparameters. You don't have to actually code this in yourself. It's exposed in the software, and it integrates seamlessly into our existing VPI design suite. So yeah, feel free to reach out. Thank you for your attention. We're happy to put on a free demo. I see a few of our users in the participants list. So if you want to evaluate the software, feel free to reach out to me. My email's here. I guess one thing I'm interested from the audience is, are there any specific applications you'd like to see as well? Yeah, we're actively developing our application example library. So thanks for your attention.
Thank you, Chris. Yes, let's ask the audience. So, what are your questions for Chris, and especially the users of these solutions from VPIphotonics? Please push the raise hand button. Anyone?
I couldn't have explained it that clearly. So if anyone's interested in trying it out, feel free to reach out to me. Send me an email if there's questions as well.
Yeah, no, but that was indeed very clear. So did you say it's already issued on the solution?
Yes, we made the announcement at ECOC this year, and we just released it to our customers maybe about a month ago. So it's brand new.
Okay, and what is the distribution model?
It's an add-on to VPIphotonics design suite, so we provide subscription licenses for that as well. It looks like there's a question.
Yeah. Let's go to that one. Sarmad from NGC.
Please. Yes. Good morning. Thank you, Chris. Good to see your presentation here. So I'm interested in evaluating this. I have a few applications in mind, and I can reach out to you later. So for sure.
Great. Yeah, appreciate it. Look forward to connecting with you again.
Thank you.
Okay, good. We found one user. Okay, thank you, Chris. I will pass now the word to the next speaker then, Lars Antje, the CEO at Silicon Light Machines. Will tell us about high power and ultra fast switching multi-beam optical head for laser processing. Lars?
All right. Thank you. Let me share my screen. Can everyone see this?
Yes. Okay, full screen mode. Go ahead.
All right. Great. Good morning. I'm Lars. I'm the CEO of Silicon Light Machines, and today I'm going to talk about our planar light valve technology. And we have a multi-beam optical head for materials processing as our application. So Silicon Light Machines, we're a subsidiary of Screen Corporation in Japan, and we make grating light valves, and Screen makes tools around our grating light valves. So the movie on your left shows a commercial computer-to-plate printer using our grating light valve that uses an 808 nanometer grating light valve, and the output is a 2400 DPI plate setter with very high throughput. The movie on the right that's playing right now is a direct imaging tool for advanced packaging. That is the movie should go on?
Actually, it's not. Maybe you need to click on it.
Interesting.
That's good.
Okay, so now so the movie on the right here is showing the Screen direct imaging tool that uses our UV grating light valve that has 8,192 channels, and this tool prints 2 micron minimum feature size, and it produces 65 wafers per hour. So it's a high throughput tool. So that's kind of a background on Silicon Light Machines and Screen. So our new technology is called the planar light valve, and in this application, we're using the high power abilities of the planar light valve. So on the left, you see the grating light valve. It's a pixel structure based on ribbons, and it's a one-dimensional modulator. And we've evolved that to a two-dimensional structure, a piston-based pixel structure that we call the planar light valve. And it does many things very similar to the grating light valve, and there's some obviously some differences between the two. Specifically now for this application, we're interested in making a very high power optical modulator. And the grating light valve actually isn't bad. It can modulate 100 watts of IR power, but that's about the limit. And the limit's because of the very narrow active region. So it's a very kind of a small active area, and it's the power handling is limited by heating. The PLV, on the other hand, can make an arbitrarily large active area. And so with this, we can illuminate these large areas with up to 1 kilowatt of laser power. So we can go from 100 watts to over a kilowatt in optical power modulation. For materials processing applications, the line beam is actually a very nice way to operate it. So we've configured this PLV modulator in a linear drive configuration, and as I said, that's ideal for high power scanned line systems. This shows the kind of a schematic of the PLV in action. So the PLV creates a linear array of beamlets that can be modulated at frequencies up to 200 kilohertz. Just as a side note, the higher the pulse energy from the input laser, the larger the swath width is. So this shows that we're stitching 3 swaths together on the workspace. And if we had higher laser energy, then this swath could be larger and even be a single pass device. The center picture shows the linear array of beamlets, the swath, as this QR code is being printed. So the QR code is printed on stainless steel. This is our product. It's an optical head that includes the PLV. It includes the optics in order to illuminate the PLV. So the laser comes in on here. We've got beam shaping optics, illumination optics, shape the beam properly to illuminate the PLV. And then we have projection optics to turn this PLV into a line image over here. And then with relay optics, we can relay the line beam onto the work surface. The system has an integrated calibration unit. So in fact, this calibration unit can calibrate your whole optical system. So any other non-uniformities in your laser illumination, for example. And so the specific configuration we're starting with is for stainless steel marking applications. And so we have a 1064 nanometer picosecond laser. The output of this device is a 2.7 millimeter swath length with 130 beams, where each beam is 20 microns, has 20 micron spot size. The fluence is 0.6 joules per square centimeter. And we have the option to put in a galvo scanner. And typically would choose between a galvo scanner or physical motion of the media. These are some scanning methods. On the left, a traditional XY stage. We'll show you how we do that with our demos. Galvo mirrors work just fine as well. And for very high throughput applications, if the swath size can be tailored to the image size you want and the media is flexible, we could do a very high throughput roll-to-roll system. So the advantage of the PLB is really throughput at high resolution. On the right here, we have a table where we've done some estimates of comparing our multi-spot beam system with a single spot system, and for various resolutions. I won't go into all the details, but the bottom line is the higher resolution, the better performance our optical head is compared to a single spot. And roughly, you can get for 4x the resolution, you can get greater than 10 times the throughput. Another advantage is that the average power per beam can be less than these single spot beams and can be a little bit gentler for heat sensitive materials. So a couple of applications or demos. This is a additive manufacturing system demo built by our parent company Screen. And the input to this optical head is actually a CW laser at 1070 nanometers. And so we have 500 watt beam coming in, out comes a multi-spot beam, and we relay that spot beam onto the work surface. And so for traditional additive, this is for polymer additive manufacturing, you lay out a bed of polymer material, and then the beam comes across and selectively melts the material as needed for each layer. This is a demo of that system. It's showing, you see each swath coming across the beam, coming across the screen, and then there's a new bed of powder put down, and the process repeats itself until the final part is built. And so the advantage here is it's a high resolution polymer system, high throughput, and that's one of the two applications we're showing today. The other application is laser black marking, so black marking stainless steel. This shows this is a demo system that has a 20 watt picosecond laser with 100 microjoules of beam energy. And so we can get 50 beams out of this system with a swath width of 1 millimeter. For our product, the laser power will be greater than 100 watts. The laser energy will be 200 microjoules. We'll have 130 beams and a 2.7 millimeter swath, so much higher throughput even than this demo. We can mark, kind of lots of different things. We do QR codes. We've done logos. We've done text. We've done images. That's my dog. And overall, you can see, I think if you look carefully, the quality is very high. I mean, we come from a heritage of 2400 DPI printing, and I think it shows in the quality of these prints. So in summary, we're building a high throughput multi-beam optical head suitable for laser processing. We have excellent image quality, high resolution, superior throughput, and we can customize it to support various applications such as stainless steel, plastics, and other materials. The range of wavelengths we work at are anywhere between 355 nanometers and 1064. We can work with picosecond, femtosecond, nanosecond pulse lasers, as well as CW lasers. We have an integrated calibration unit into the head, and we can add a galvo scanner, and we can connect with, synchronize with XY stages or roll-to-roll. And this product, in the process, we just finished the design. We'll have our first product release in July of next year. For more information, we'll be at Photonics West, paper called High Throughput Spatial Light Modulator Based Multi-Beam Marking System. If you want an overview of our technology, this is not enough time for me to give you the overview of the technology. Please go see this YouTube link, and please come give me a call or send me an email. Thank you very much.
Yeah, thank you, Lars. These were quite impressive applications you've showed us. Are there any questions in the audience? Just use the raise hand button. I was actually wondering, Lars, myself, can the same type of optical heads be used in lithography type of patterning with a multi-beam for multi-beam lithography?
So, the first, yes, it can. I mean, the first slide I showed you was an actual lithography tool, multi-beam lithography tool that has 8,000 channels. So it doesn't require the power. What's different about this is really the additional, high power aspect of it. So we can put, kilowatts of power on the modulator as opposed to 100 watts. So typically lithography doesn't need that much power.
Right. Right, it's a high power optical head, indeed.
Yep.
Okay, anyone else? If not, I suggest we thank Lars again, and we pass to the next speaker, who is Antje Thamm, sales director at Optronic, who will tell us about the SMD LEDs with a specialty developed narrow beam lens for homogeneously illuminated spots.
Yes, thank you very much. Good evening. You can hear me? Yeah,
yes.
Yeah, okay. So my name is Antje Thamm. I'm the sales director of EPIGAP Photonics, and I'm here in this session together with my colleague Frank Lerch. He's the director of business development. And yeah, I would like to say thank you for the opportunity to talk to you and to talk about our new product, this special SMD with narrow beam lens for homogeneous light spot. And my first slide is to introduce our company and technology. And so I have to move to the next slide, but oh, sorry. Interesting why this doesn't work.
Maybe you try to unshare and then share again.
Okay.
Maybe just a bug.
Mm-hmm.
Usually it helps.
Okay, so now it was too fast. So we are well known in the semiconductor market for our LED chips production, and you can see two pictures of our production in the top line, and we are also well known for our SMD production, and two pictures on the bottom line. To give you a kind of impression, we see our strengths in customization and realization into sophisticated products. Our production is located in Berlin, in Germany, and we are working with 80 employees on about 830 products. For this, we have 3 different clean rooms, and in the first clean room, we have the complete chip production. We are working with A3B5 semiconductor material, and this gives us LED chips in the visible range and in the near infrared range up to 1720 nanometers. The main steps of our technology are metallization, the photolithography process. We are doing 100% testing and binning. And we are checking spectrum, peak wavelengths, output power, and forward voltage from every chip. After testing, we have the following steps with dicing and test and qualification. In our second clean room, we have the automated SMD production line with products in the range from 225 nanometers up to 1720 nanometers. So we cover a wider range here. And in our third clean room, our assembly of customized chip-on-board modules is located. The various products we are producing have certain shares in the overall product range, and we have a strong focus on our SMDs, as you can see here. And here we have the applications, and one of the applications is the industrial sensor. And our new product development is also in this area and targets also the industrial sensor market. A special sector of the industrial sensor market is the optical encoder market, where we usually use an TO packaged LED, which shines through a diffractive grating, and the photodiode array on the other end detects the passage of light and generates a corresponding electrical impulse. For a highly precise measurement, a homogeneous light spot is required, a narrow beam emission, and also important for this application is a temperature range from -40 degrees Celsius up to +125 degrees Celsius. The market is required a cost reduction of the unit price, and the production is mainly manual, so our capacity is limited from 100,000 pieces to 200,000 pieces per year. And the development is addressing an alternative illumination. And therefore, we start thinking about an SMD solution. And the next slide, I present the steps and results of this development. So normally, if we are talking about an SMD, this narrow beam emission is difficult. And so we started an optical calculation and simulation and find out that a double lens array can give us a really narrow beam emission. After this calculation, we started with the mold making for the lenses. The next step was lens shaping, and then a sample production run starts. And we fixed our SMD chip as usually on an aluminum nitride ceramic based substrate. And the results of this new product were really good. So we already reached out also a homogeneous light spot. This is the emission, the view angle emission. We got a narrow beam with 6 degrees. We have a spot diameter of 4 millimeter. We reached also an equal output power comparing to the TO package. And the temperature range was also in the required range. And this product is automated solderable, so a big advantage for the customer. We reached with this way a cost reduction by 40% of the unit cost, and we can increase the capacity up to 500,000 pieces and more per year. So we designed an open platform also for other applications. It's not only good for optical encoders, it can be also used in applications with comparable requirements of narrow beam. Yeah, so this leads me to the last point. So if you like to get in contact with us in person to talk about your application, so you can meet us next time and next week already at OASIS conference and exhibition in Israel. And you can also meet us during the Photonics West show in San Francisco end of January. So glad if you have some questions to us. Thank you for your attention.
Yeah, thank you for your presentation, Antje.
Yeah.
And now it's open for questions from the audience. So just feel free to raise your hands. Yeah, Sergio from Laserpoint, please.
Hello, Antje.
Hello.
Just a quick stuff. Did you do you have plans or evaluate to fiber cap to use these optics to fiber couple?
Not yet. I know that often there is a huge interest in fiber coupling, but we didn't try it up to now.
Thank you.
Okay, thank you for the question, Sergio. And Antje, thank you for your presentation. I'd like to pass the word to our last speaker, as also our time is running out. So the last speaker of the session is Masayo Izawa, sales manager at SCIVAX. Hello, hi. Masayo. Yes.
Hi, hello, can you hear?
Yes, we can hear you.
Okay,
just share your presentation and we can start.
Can you see my screen?
Yes. Maybe just make it full screen.
Okay. I think it's not working. I don't know why. Is that okay? Not full screen.
It's okay, but it's not full screen.
Okay.
That's okay.
Okay. Thank you. Hello, everyone. This is Masayo Izawa from SCIVAX. So today I would like to introduce our wide-angle illumination optics for DMS and XR, which called Photonics diffuser and addition dot projector. Okay, let's quickly go through our company introduction. Basically, we are a nanoimprint technology company in Japan. We have been working on nanoimprint for more than 20 years, and we provide nanoimprint foundry service in 8-inch wafer. Also, we provide nanoimprint tools covering from R&D to mass production. Last but not least, we also sell nanoimprint products. So the illumination products of today's topics are made by our nanoimprint technology. So as you know, in recent years, the demand for 3D sensing has been increasing. 3D sensing systems using time of flight are attracting attention because of their compactness, also the low CPU load and ability to operate in the dark. The principle of TOF is to measure the round trip time from the light source to the object. The system consists of the TX module and RX module. Our proprietary Photonics diffuser and addition dot projector are designed for TOF sensors TX module to control light distribution and intensity from the VCSEL to get the ideal shape of light. Recently, we have showcased our newly released wide-angle diffuser and dot projector for DMS and XR at Optronic. DMS and XR devices require wide-angle illuminations with FOI around 140 to sense in-cabin and human viewing field, but it's difficult to be realized by conventional DOE. Our Photonics diffuser and addition dot projector enable the wide FOI by combination of diffraction and reflection without any collimator lens. The picture shows a 3D image obtained by a TOF sensor system. We collaborated with Melexis using 140 and 110 Photonics diffuser. The distance of the sensor with illuminator from the human's face was only 50 centimeters, while it clearly measured the end of the stretched arms. Another 3D image also demonstrated the capability of monitoring both the driver's seat and passenger seat with one single diffuser lens. Photonics, the optical diffuser with a wider angle of illuminator for TOF sensor, is applicable for a variety of emerging applications such as automotive and XR. Not only that all of the optical components from SCIVAX are made by the cost-efficient nanoimprint method, but also with high reliability and great performance. Along with the Platanus, we also developed a new optical complement called Odysseus. By using both the reflective and diffractive functions of light to solve various disadvantages with the common DOEs. Odysseus can achieve an FOI as 140 by 110. Also integrated the collimator lens in one component so that it could achieve compactness and also low BOM cost, power efficiency, and power intensity are other benefits of Odysseus. Our customer confirmed that Odysseus has 27% better efficiency than conventional DOEs. By the combination of Platanus and Odysseus, we think this is the best solution for 3D sensing needs of automotive and XR. Last but not least, our nano imprint foundry service provides customization together with internal optical design and simulation expert, and process development can support your own customized optics for various applications. Thank you for listening. If you have follow-up questions or any sample requests, you can contact us to send emails to this email address. Thank you.
Okay, thank you, Masayo. Very interesting product you have. Is there any question in the audience? Sergio, do you have a question, or is it still from the last question? You have the hand raised. I guess means not, no?
No, still on from the last question, sorry.
Okay. So Masayo, so are you distributing this all around the world?
Yeah, of course.
Okay. Do you already have customers in Europe?
We have customers in Europe too. Yes.
Okay. Well, let us know, how EPIC can help you to distribute that even further within Europe. And we have a question from the workshop of Photonics. Lucas, please.
Hi. Thank you for the presentation. It was really interesting. And I have a question. Do you organize any panels to showcase your products in any of the bigger events, photonics industry, like Photonics West and similar?
Yeah. We are going to Photonics West next year, January.
Okay.
Yeah.
All right. Maybe I'll see you there.
Thank you.
I'm actually interested. Thank you.
Thank you.
Yes, exactly. So I think most of us will see each other at the Photonics West. So and that will be our next meeting point, because with the presentation of Masayo, the session is closed for today. Please fill in the poll that now appeared on your screen, and just a few final words from my side. So this was the episode of EPIC's member new product release, and so we have heard from 6 EPIC members: Hummink, Laserpoint, VPIphotonics, Silicon Light Machines, Optronics, and SCIVAX about their new products. I'd like to just remind you that EPIC helps you with technology consultations, market reports, networking events, access to new markets, mentorships, HR support, and investment. And so now you're following one of our online events, and here on the screen you can see the full list of the events of the end of 2023, end of 2022, beginning of 2023. And in yellow, I just highlight for you the upcoming online events that you can still attend in the upcoming 2 months. There is one dedicated to workshops, to a workshop given by investors, and an online technology meeting on metamaterials and meta lenses, as well as online technology meeting on laser-based manufacturing for implants. And with that, I'd like to thank the speakers of today's session again, and see you next time.
Thank you. Bye.
Thank you very much.
Yeah, thanks. Have a good day.
Bye.
Very much. Goodbye.
Bye-bye.
Bye bye.
Thank you. Bye.
Thanks, West.